Last speaker for today is Kęstutis Česnavičius from CNRS and Université Paris-Sud, and he speaks on purity for the Brauer group of singular schemes.
Thank you very much, and thanks to the organizers for the invitation to speak at the conference. I would like to discuss the purity for a Brauer group, in particular in situations where the scheme in question has singularities, complete intersection singularities in particular, is joint work with Peter Scholze. The point of departure is the purity theorem for the Brauer group of regular schemes. So let me begin by reviewing that. The purity for the Brauer group was conjectured by Grothendieck and proved in many cases by Gaber over the years. And in some remaining cases in mixed characteristic, it was settled by introducing a perfectoid approach to questions, to purity questions. And the statement precisely is as follows. If one has a Noetherian regular scheme, Noetherian regular scheme X. So this means that local rings of X are Noetherian local, well, are regular local rings, and a closed subscheme of codimension at least 2, closed subscheme Z in X of codimension at least 2. Then the Brauer group, the cohomological Brauer group of X, does not change if one removes this closed subscheme. More precisely, the pullback map from the Étale cohomology H2 of X with GM coefficients to the same cohomology of the open obtained by removing Z is an isomorphism. So let me mention right away that the injectivity of this map is simple. It was established by Grothendieck himself in the articles where he posed this question, and more precisely, he showed that the groups are torsion. So I am allowed to omit the torsion subscripts usually present in the cohomological Brauer group, and more precisely, if one has a Noetherian regular scheme, Noetherian integral regular scheme Y, then the pullback map of H2 of Y with GM coefficients to the similar H2 of the function field of X is injective. And this Étale cohomology group, because the scheme is a field, identifies with Galois cohomology, and Galois cohomology in higher degree is always a torsion group. So the H2 of the global scheme is torsion itself, and this injectivity also shows the injectivity of the taro, and the surjectivity is significantly more subtle, and we'll discuss it in this talk. But let me just give an example of an arithmetic situation in which this kind of thing applies. For instance, if one has a finite type smooth scheme X over the ring of p-adic integers, then if a Brauer class of the generic fiber of X extends, well, a class alpha of the generic fiber Brauer group extends to a class alpha tilde of the model of the Brauer group of the model, regular model, if it extends over the generic points of the of the special fiber. Well, of the special fiber, like so. So if one has this spec ZP and our scheme, non-singular scheme, regular scheme X over spec ZP, and one has a Brauer class on a generic fiber, then it extends to the entire integral model if and only if it extends over the generic points of the closed fiber. Sorry? Sorry. Thanks. All right. And and in this talk, I would like to discuss a similar statement in case when x is possibly singular. The main result for the Brauer groups in this case, I'll state here as theorem 2, although I forgot to number that one, is what I'd like to report on. If we have a Noetherian scheme X and a closed subscheme Z as before, but now, okay, so, and a closed subscheme Z in X of codimension at least 4 now. Previously we had codimension at least 2, now the codimension is at least 4, such that X is a complete intersection along this scheme Z, more precisely, such that for every point Z which lies on our closed subscheme, the local ring of X at Z is a complete intersection, and more precisely, that means by definition that the completion of this Noetherian local ring is a quotient of a regular local ring by a regular sequence. Okay, so of course regular X satisfy this, and more generally, for instance, X could be complete intersection in projective space is something that satisfies these assumptions. Then the conclusion is that the cohomological Brauer group of X does not change if one removes this closed subscheme Z. And now I put the torsion, because these groups are not a priori torsion. Okay, so it's the same conclusion as before, except X is now allowed to have singularities which are complete intersection singularities. And as I've mentioned, X could be, for instance, a complete intersection in projective space.
You don't assume like regularity away from Z or anything?
No. So yeah, just away from Z, the scheme X is not required to have, any assumptions. In fact, this is really somehow a statement along Z. One can even drop like a Noetherian S and assume that the complement is retrocompact in X, but still its assumption holds, and then one has the same conclusion. It's somehow really the phenomenon is happening along X, so the singularity somehow, yeah?
In relation to the remark, is it still torsion even if you don't assume it's integral?
Well, a regular scheme is somehow a disjoint union of its connected components, and so therefore somehow, yes, if you define torsion to mean that it's killed by a locally constant function on the scheme. Otherwise, well, yeah, but anyway, this. No, and and in the setting of theorem 2, these H2s really can be non-torsion, so it's important to put.
Would the theorem fail if you didn't write torsion?
Yes, I think so. Yeah. Okay, so let me make some remarks. Yeah? So, yes, yes, the codimension assumption is sharp. If codimension is free, then there are counterexamples. For instance, I think, so for instance, one can have a curve over a finite field, then one takes a cone over that curve and looks at the vertex of the cone. That's two-dimensional. Now one can somehow consider line bundles on the punctured cone, and then afterwards one takes like 2 power series variables mod odds by xy, and that increases one does some sequence. Okay. So one gets a counterexample like this from the eventually from line bundles on curves over, say, field. So the codimension assumption is shown here. Okay, so the first remark is that this theorem 2 implies theorem 1. Well, if codimension of Z upstairs is at least 4, this is evident, and in low codimensions somehow indirect. I mean, maybe except for the case of codimension 2, which is anyway not difficult. And indirectly in codimension 3. But anyway, as we see, somehow the proof of this theorem is in some sense an elaboration. I mean, it builds on similar ideas as that were used in the theorem above. So this really is, I mean, it's bad to prove theorem 1 like this. And the second point is that the underlying statement is local in some sense. More precisely, what is really going on and what is really that we're proving is that cohomology with supports, flat cohomology with supports in this closed subscheme of X with mu n coefficients for any integer n vanishes for I less than the codimension of Z in X with a complete intersection assumptions as there. And of course, these firstly, since we're considering torsion groups, then this is really a statement about mu n in some sense. And then the pullback map, its kernel and co-kernel are controlled by cohomology with supports groups. And so if we manage to show that these cohomology with supports vanish in the, well, for degrees less than 4, we need H3 to get search activity, then we're done. And it's in fact, okay, so that's what really we're going to prove. And in fact, once we have this reformulation, once we have this reduction, then by the local global spectral sequence for cohomology with supports, plus a little bit of the visage in a form of, well, okay, this vanishing, it reduces to its local case. It reduces to a case when X is strictly local. So it's a spectrum of a strictly Henselian Noetherian local ring, which is a complete intersection. So okay, X is strictly local. And the closed subscheme Z is just a closed point. Okay, this is formalism of cohomology with supports that somehow tells that one can work locally to get this somehow vanishing in low cohomological degrees. It suffices to do it locally, and then we do it at a locally, and it's slightly non-trivial because if we just localize at a closed point, if we just localize X at a point that lies in Z, then the local closed subscheme need not be just a closed point. But anyway, that's where this Devasage things comes in that I'm not really explained. Okay, and so for the rest of the talk, I will really be discussing this local statement. And in fact, it itself, in turn, is a special case of a much more general purity phenomenon for flat cohomology that is not really about mu n in particular, but about any finite flat group scheme, commutative. Okay, so to introduce the latter, okay, so let me discuss then purity for flat cohomology, which is really what is going on. I say flat cohomology, but of course, if n is invertible on X, then one can work with a tau cohomology. In this case, significantly easier. And to explain the statement, let me put it in analogy with a theorem of Gaber from 94, although later he gave additional other proofs. This was the absolute cohomological purity of Grothendieck, and it's a purity statement for a tau cohomology. More precisely, the statement is as follows. If one has a regular local ring R with maximal ideal M, and one has an integer n invertible on R, then the tau cohomology with supports in the maximal ideal of this ring R and with coefficients in Z mod n vanishes for I less than twice the dimension of the ring. And this absolute cohomological purity for a tau cohomology immediately implies statements of extending global cohomology, global tau cohomology classes past closed subschemes of sufficiently high codimension. And it's really in the same vein that we're looking to, I mean, it's the same kind of phenomenon that we're looking to understand there. And so the main result really is a version of this for flat cohomology. If we have a Noetherian local ring, okay, R with maximal ideal M, that is a complete intersection. In the sense I recalled previously that the completion of this ring is a quotient of a regular ring by a regular sequence. In fact, the case where R is regular is already interesting, but anyway, we want to do singularities there, so it definitely we should maybe include complete intersection. And we have a commutative finite flat group scheme, R group scheme G, then the flat cohomology of this ring R with supports in the maximal ideal and coefficients in G vanishes for, in cohomological degrees, less than the dimension of the ring. So this, okay, this, for instance, G could be mu n, and if R is of dimension at least 4, then we would get the vanishing, certainly in cohomological degrees less or equal than 3, that a purity for a Brauer group of singular schemes would follow. So really, this is what we're searching to prove. And okay, the Brauer group case is then just a low degree case of this. Here it is the dimension of R, whereas here it was twice the dimension of R. And let me illustrate right away with an example of what is going on in this flat cohomology of why we're getting only dimension of R rather than twice the dimension of R. I mean, in a tau cohomology, it has to do with that we're doing complete intersections, I mean, and not a regular case, so singularities. But more precisely, this vanishing is somehow related to depth phenomenon. And so, for instance, let me consider a case when R is an FP algebra, and our group G is just Z mod P or alpha P. Then, okay, so let's consider this case. Then, because our ring R is a complete intersection, so in particular it's Cohen-Macaulay, its depth equals a dimension, and that means by the cohomological characterization of depth from SJ2 that the cohomology of supports of R with coefficients in the structure sheaf, in GA in other words, vanishes for I less than a dimension. And so we get from Artin-Schreier type sequences that also the flat cohomology with Z mod P or alpha P coefficients of this complete intersection vanishes for, again, for I less than the dimension of R. So what is going on here is that there's a definition of depth, which is just in terms of vanishing of this local cohomology group. In general, it's for I less than the depth. And okay, if depth equals the dimension, we get that. And then, I mean, we see that this follows right away. And so somehow this flat cohomology purity phenomena really have a lot to do with depth. And that's why we're getting just a dimension rather, I mean, rather than, we cannot expect anything better because of this example. I mean, the depth is always less or equal than the dimension. Okay, and let me make some remarks about special cases of this theorem that have been considered previously. So firstly, the case when the order of G is invertible in R was known. In this case, this really is étale cohomology because G is étale, and so one can use étale cohomology with supports. And this is due to Gaber. He deduced it from his. Well, there are several ways to deduce it from this theorem in a non-singular case. And there have been other. Well, there have been low-degree cases that have also been considered previously. So the cases of cohomological degrees 2 and 3, the cohomological degrees that are most relevant for this Brauer group problem, with G being equal to mu n, these cases settle conjectures of Gaber. So Gaber made made conjectures which amount to low-degree cases of this goal theorem, and in fact he made those conjectures in relation to his search of a strategy for purity for the Brauer group. His strategy was to first prove purity for a Brauer group in a complete intersection case, and then deduce it for regular schemes. And the insight of why complete intersection is somehow why it may be advantageous to make the problem more difficult in this way is that if one has a complete intersection and one reduces modulo P and P is a non-zero divisor, then one still gets a complete intersection. And somehow by this, he then tried to reduce to positive characteristic and using this kind of strategy. Whereas if one has a regular ring and reduces modulo P, then if it's ramified, then of course it's not going to be regular. Yeah?
In case 1, do you get the less than twice the dimension?
No, in case 1, one still gets less than a dimension. And there, it's the singularities that are causing that. Roughly speaking, there's some local Lefschetz theorem, which, and the local Lefschetz isomorphism range is roughly the dimension. And that's why, okay. All right, so let me give just a concrete example of what one of these conjectures of Gaber were. So for instance, we get that if we have a local complete intersection of dimension 3, okay, local complete intersection R with maximal ideal M of dimension 3, then the puncture spectrum of R has no non-trivial torsion line bundles. And of course, if the dimension, okay, so let me just say it in words. If the dimension is at least 4, then the torsion restriction is not necessary. And this is a Grothendieck-Lefschetz theorem from SGA4. This dimension 3 case that was conjectured by Gaber is a strengthening of that. Well, I mean, it's an extension, mild variant of that Grothendieck-Lefschetz theorem. And this, in fact, is the first case in which there have been special cases proved in the literature of this result. But to prove it in general, it really seems that, I mean, I don't know how to do it. That wouldn't involve some of the ideas that go into the proof of that theorem 4 that I stated there. Sorry? Which torsion? You mean if you knew that the torsion is divisible, would you be able to show that it? I don't know. A priori, no, I don't know. Okay, so let me move ahead with discussing some of the ideas that went into proving this purity for the Brauer group in the regular case, and we will see the points in the proof that do not adapt to the complete intersection case, and this will lead us to discussing new inputs that are needed for theorem 4, and then we'll discuss these new inputs in greater detail. So. Okay, so let me review the proof idea for theorem 1. This was purity for the Brauer group, just regular rings and extending past closed subschemes of codimension at least 2. And here, so the idea is to use perfectoid rings. Let me just recall a definition because it's sufficiently simple. A p-torsion-free ring A is perfectoid if the following, well, is perfectoid if it is p-adically complete. It's one basic requirement. And if there exists an element pi in A such that the pth power of pi divides p and A mod pi is isomorphic to A mod pi to the p via the Frobenius map. Okay, so if we have a p-torsion-free ring, it's quite simple to say what it means for it to be perfectoid. It needs to be p-adically complete, and the divisor cut out by p needs to have this pth power root in the sense, I mean, or more precisely, there should exist this kind of element such that modulo p and modulo pi and modulo pi to the p, these isomorphic rings via the Frobenius. Okay, now there's a basic fact of commutative algebra, really, that says that if one has a complete regular ring, complete regular local ring R with maximal ideal M, such a ring always has a faithfully flat cover by a perfectoid ring. There is a faithfully flat map from R to a local ring R infinity with its maximal ideal M infinity, such that R infinity is perfectoid. And in fact, this R infinity is up to forming p-adic completions, a filtered direct limit of regular rings. A filtered direct limit of regular local rings, which are in fact finite flat R algebras. Let me give an example of what is going on really. So we have, for instance, R could be the Witt vector ring of an algebraically closed field of positive characteristic P with some free variables x1 up to xn, and then for such an R, the ring R infinity, for instance, could be chosen to be obtained from the original one by adjoining all p power roots of P and all p power roots of all the variables. Okay, so this fact is true as stated even if R is p torsions, if R is an FP algebra. However, I mean, okay, so I only gave a definition of perfectoid ring for p torsion free rings. If A is actually an FP algebra, then a perfectoid ring is just the same thing as a perfect ring. However, there are cases in which the ring A is not an FP algebra but has p torsion, in which also there is a definition of what it means to be perfectoid, but that definition is significantly more subtle, and I don't want to give it. So that's why that's why I assumed it's p torsion free. But if it's an FP algebra, perfectoid just means perfect. Yeah, so of residue characteristic P. Greater than 0. All right. Okay, so we'll use this fact and to see how the proof of theorem 1 goes. So let's see what we have and what we want. So what we have is a regular local ring R with maximal ideal M of residue characteristic P and dimension at least 4. And what we want to show is that okay, so let me also assume for simplicity that it's strictly Henselian. So in this crucial local setting of purity, we have this regular local ring of sufficient large dimension at least 4. In the original conjecture is dimension at least 2, but dimension 2 is not so difficult from Most-Landau-Buchsbaum theorem, and dimension 3 was done by Gaber. Anyway, let's assume it's dimension at least 4. Then what we want to show, yeah? It is not trivial, but it was known a lot earlier, and it's really part of a different phenomenon, part of a Satal cohomology, absolute cohomological purity for a Tal cohomology. So the equal characteristic 0 case, I mean, it was known a lot earlier, and I just don't want to discuss it because it's part of a study of a Tal cohomology, really, not flat cohomology. So I'm focused on this, on somehow the most difficult case in this. In this story. Okay, so and what we want to show is that H2, a Tal cohomology of the puncture spectrum of R, is trivial. all right? Then because the similar H2 for R is trivial, then we will get purity. It doesn't change if we remove the maximal ideal. Okay, so how does the proof go? So this fact that a regular ring can always be covered by a perfectoid ring, which in fact, up to p-adic completion is a limit of regular rings, this fact reduces, I mean, using this fact, one can reduce to showing that similar H2 in a of the perfectoid ring, perfectoid local ring, vanishes. It's just, I mean, there's some spectral sequence argument, and first one needs to pass to completion. But anyway, this one can do this, and so now one needs to show this. Then we reduce to. Then we use a trick. Our R was regular, so it suffices to show that this vanishes if we invert P. So because R was regular, these H2s always inject into similar H2s where we consider the fraction field. And so if we manage to show the vanishing after inverting P, that's even better. This vanishing would follow. A priori is okay. So it's a trick that won't work for complete intersections. Then we use the tilting equivalence of Faltings and, well, of Scholze, or almost purity theorem of Faltings and Scholze, to reduce to showing this. So where okay, so this is some perfectoid ring, and it has a tilt, which is a perfect FP algebra. So whatever this is a perfect FP algebra. And the tilting equivalence, which I'm using for this step, is saying, roughly speaking, that the étale cohomology of a perfectoid ring, perfectoid QP algebra, does not change, is invariant under tilting. That's somehow the whole, okay. So this mu p flat is some finite étale group scheme over this ring. Now, since we inverted P, mu P becomes étale, and this is étale cohomology. So we use tilting. We reduce to positive characteristic. We now need to prove this, where we don't really know so much about this mu P flat maybe, but now what we use is simply use. Sorry? Yes. Yes, it's étale, and that is because our mu p after inverting p it itself is étale. So mu p over a ring with p inverted is a finite étale group scheme. So under tilting equivalence, there corresponds a finite étale group scheme in positive characteristic. For instance, if our ring contained just p roots of unity, then mu p would just become zp after inverting p, and this would also be just zp. But in general, there's some, well, some descent, and like you tilt the descent, and you get the.
So it looks nothing like.
Sorry?
Is it one-dimensional? Is it twist of mu p?
Well, it is. What do you mean one-dimensional? It's like zero-dimensional. Yeah, it's like one-dimensional as an FP vector space. Like it's of cardinality P, just like mu P. Okay, and now we use that the P cohomological dimension, étale cohomological dimension of any FP algebra is less or equal than 1. It's a fact from SGA4 proved by Michael Artin. Just like for fields. For fields of positive characteristic, their P Galois cohomological dimension is at most 1. Same holds for any affine scheme, and so therefore we get the vanishing. It's just that in positive characteristic. Okay, and so let's then discuss the singular case when we have complete intersection singularities and our group scheme is not necessarily mu p, the general case. And let's try to analyze which parts of this argument really need. I mean, why can't we just do the same and somehow conclude? So firstly, okay, so we'll discuss complications in the LCI case, or okay, yeah, in the LCI case, even for mu p, they are there. And so if we want to prove this theorem 4, this purity for flat cohomology, or even theorem 2, purity for the Brauer group with complete intersection singularities, then we can no longer invert P, because we used that. I mean, this was a trick that the Brauer group it injects into a Brauer group of a function field. So we cannot. I mean, we can no longer do that. Okay, so we can no longer invert P, and somehow need to work integrally. Now, integrally, there surely is, I mean, and we need to work in particular with flat cohomology. Another trick was that mu p became a tau. So we need to work with flat cohomology. And for flat cohomology, there surely is no such thing as like tilting integrally. So we need to do something different. Moreover, okay, so R is no longer regular. Yeah, it's now singular. So R infinity is also no longer perfectoid, but it's only a quotient of perfectoid by a regular sequence. So okay, so that is also somehow a problem. Thirdly, the passage from R to R hat to the completion is no longer available. I mean, I didn't really discuss this passage, but it's a step in there. And for Brauer group, one can make this passage, but for flat cohomology, especially in the higher degree, it's I mean, it's no longer there. If one assumes that R is excellent, then one can get around this problem just by using Popescu desingularization. But anyway, that's an assumption that should not be there in the theorem, and so we need to deal with that. And the fourth problem, which is kind of a bit technical, is that R is no longer p torsion free. So p torsion non-zero is possible, and with R still being of mixed characteristic, R could even have several branches, for instance, and so we need more general perfectoids than what I discussed in than the definition I gave. Okay, well, this fourth difficulty really just means that we'll have to work harder, but the first three, to resolve them, we really need to introduce some new ideas to this. So to overcome these, we proceed as follows. So for the first difficulty, we replace tilting. We replace the tilting equivalence for a tau cohomology by Dieudonné theory in perfectoid setting, more precisely by Dieudonné theory in the setting of prismatic site and prismatic homology of Peter Scholze has recently been developed. Okay, we'll discuss this. And some classification results for finite locally free group schemes over perfectoids, just as we have over perfect rings, perfect case due to Gaber Berthelot, in a mixed characteristic case due to Lau and Scholze, and also work in progress of Lebrun and Anschutz. For the second difficulty of R being no longer regular and R infinity effectively no longer being perfectoid, to tackle this difficulty, we use Anglais lemma, or more precisely, we need some general version of Anglais lemma, which we show. We show an insymptomic version of Anglais lemma. Anglais lemma originated in his proof of the direct summon conjecture in commutative algebra using perfectoid methods, and now one can give a very general version of this lemma. And here we're generalizing a version of this lemma given by Gaber and Romero. And this is something I won't really discuss. Okay. The third point to pass to the completion, and in fact later to pass to p-adic completions, which also is kind of a problem later when we need to p-adically complete our limits to get perfectoids, we show excision for FPPF cohomology. More precisely, we show that in the setting of the this theorem 4, that the FPPF cohomology with coefficients in G with supports in maximal ideal is insensitive if we replace R by R hat. In fact, there's a more general statement that I hope to discuss at the end of the talk. And this, for instance, in the case when R is just a where R is just a Henselization, say, of a number field at the prime, this has recently been shown by Hariri and Demarche in the reproof of the Artin of Milne duality and positive characteristic. Anyway, it's really part of a general phenomenon that one can show for flat cohomology. Okay, and so given these, let's discuss the perfectoid version of this theorem 4. Let's discuss the statement to which really we reduce using these points 2 and 3. Okay. So the theorem that we need to okay, so these 2 points, these reduce theorem 4 to this theorem 5, which says the following. If we have a perfectoid ring A and a closed subscheme Z, which lies in the p equals 0 locus of spec of A, P being the implicitly fixed prime, if there is a regular sequence A1 up to AD in A that vanishes on this Z. So Z really is like this maximal ideal, M infinity in the applications. That vanishes on Z. So if the perfectoid has enough depth, then for any commutative finite locally free group scheme, locally free A group G of p power order, the flat cohomology of A with supports in this Z and coefficients in the group scheme vanishes for in cohomological degrees less than this depth bound that we assume, less than this depth that we have along Z. Okay, and so to prove, for proving this theorem 5, we use this prismatic Dieudonné theory. Let me overview roughly how it goes without too much detail, in fact, but anyway. So as I've alluded to, over a perfectoid ring, one can classify such finite commutative locally free group schemes of p power order in terms of their Dieudonné modules, in terms of their, well, Dieudonné crystals, really. just like one classifies finite flat group schemes of p-power order over a field of characteristic, of a, say, perfect field of characteristic P in terms of Dieudonné modules, there's a generalization, and this generalization in mixed characteristic says the following. Is okay, so this is due to Berthelot-Gaber in positive characteristic, and Eikelau and Scholze in mixed characteristic, and the link with prismatic homology is the work in progress of Anschutz and Lebrun. Okay, so collaboration, Lebrun. Okay, the statement, so A is a perfectoid, as we had. A flat is its tilt, which is nothing else than the inverse limit perfection of A modulo P. For instance, if A is just a perfect FP algebra, A flat is itself. And then A inf of A is a Fontaine's period ring, is a Witt vectors of A flat. If A was perfect, this is just the Witt vectors of that original perfect ring. And we fix Xi, a generator, fixed generator of the kernel of Fontaine's theta map from A inf back to A. So rejection in prismatic terms, we fix an so perfectoid rings correspond to perfect prisms, and we fix an orientation of that prism. Okay, so given this, there's an equivalence of categories between commutative, finite, locally free A group schemes G of p-power order. So these groups whose cohomology we want to understand, whose vanishing of cohomology we supports, and the depth properties we want to show, equivalence of categories to their Dieudonné modules, which more precisely are p-torsion modules over the A inf of A. Let me call it M. Of projective dimension at most 1 that come equipped with Frobenius linear morphism F from M back to itself. The ring A inf being a Witt vectors of perfect ring carries Frobenius, and we require a Frobenius linear semilinear morphism like that. Frobenius inverse semilinear morphism Verschiebung such that if we compose F with V, this is nothing else than multiplication by a scalar, which is a Frobenius image of the element Xi that we fix. And if we compose the other way, then it's just Xi itself. The functor G goes to this to its Dieudonné module M of G. So in fact, there are two such functors dependent on whether we want an equivariant, on whether we want covariant Dieudonné crystal or contravariant. And if we take the contravariant one, then the functor is just given by the x1 in the x1 of G against the prismatic structure sheaf of this perfectoid that we're considering. Just like the crystalline site of a perfect ring has a terminal object given by the Witt vector thickening, then so in a perfectoid case that terminal object is the A inf, and by evaluating this somehow crystal on A inf, we get our M of G. And so okay, so let me just give a very basic example. So if A is a perfect FP algebra, then then recover classification in terms of Dieudonné modules. Okay, and so using this classification and using some further results on cohomology, flat cohomology, FPF cohomology, more precisely using P complete arc descent for FPF cohomology. So descent for some very weak topology on perfectoids in this case, for the functor that sends a perfectoid A to the FPF cohomology of A with coefficients in G, we show the following formula. That our flat cohomology of A with coefficients in G and with supports in this closed Z is really described in terms of Dieudonné theory, in terms of prismatic Dieudonné module associated to G as follows. It's the cohomology with supports of the ring A inf of A with coefficients in a covariant Dieudonné module and Verschiebung invariance of this, I mean, in a homotopical sense. Okay, so now with this formula that's somehow proved by reducing to a case where A is essentially evaluation ring using this P complete arc descent, we can conclude this theorem 5, this perfectoid purity statement by depth, because we have, I mean, okay, so the key point is, the key point is that somehow we were assuming that the depth of A is along Z is at least D. Then we have that the depth of A inf is one larger, because this Xi is a non-zero divisor. Okay, so if the depth of A along Z is at least D, then because Xi is a non-zero divisor, we get one depth one larger for the ring A inf. And so now, if we want to, this is just coherent cohomology because it's just coherent module. And okay, so now if we want to show the vanishing of this in low degrees, firstly we use a long exact sequence. I mean, we use long exact sequence of cohomology to get rid of homotopical invariance like that. We just need to consider this, and then it's just characterization of depth in terms of cohomology with supports. So in some sense, I mean, it's really somehow similar argument to this positive characteristic, to the positive characteristic case that I discussed for G being ZP or alpha P, where we also got our purity just from depth. So it's just that the formalism to get the relevant formula is more involved than just an Artin-Schreier sequence. Okay, and so I want to end just by discussing a couple new properties for FPPF cohomology that we show in order to carry out this argument. First one I already mentioned, this excision. In fact, it holds more generally. So okay, so to carry out this argument, we show some properties of FPPF cohomology with coefficients in finite flat group schemes. So we fix G over a ring R, a finite locally free group of P power order for simplicity, let's say, just to fix, I guess. Usually, I mean, one can decompose into primary parts, of course, over a ring R. Then in this setting, the excision theorem, the more general version, that in fact is used in this more general form because one also needs to take p-adic completions in non-Noetherian settings, says that if we have a finitely generated ideal I in R, and the map S going to S prime of R algebras such that this map is an isomorphism along I. More precisely, if we take derived tensor product with modulo I to the n, the map induces an isomorphism between such reductions, derived reductions of okay, so infinitesimally the two rings look the same, then the flat cohomology of S and S prime are with supports in this ideal I are the same. Okay, and in fact, in fact, this holds even if one allows these R algebras S and S prime to be simplicial algebras. And for the proof, it is really important to extend somehow the scope in which the statement is made, because the reductions that are made in the proof, which eventually reduce to Dieudonné theory over perfect schemes somehow to the formula, the key formula in the perfective P algebra case, these reductions really benefit from this more general statement. Okay, there are further properties like FPPF cohomology agrees with FPQC cohomology, and the periodic continuity formula that's also important, but I'm out of time, so I'll not say them now.
Questions or comments?
Yes. Look, you need.
Can you say a few words about P-complete arc descent?
Yes. So there is yeah. Okay, so there is topology on rings where a ring mapping to another ring is called a P-complete R cover. It's a Grothendieck topology, and the condition is that whenever we have a map from this R to a valuation ring of rank 1, and the valuation ring is supposed to be periodically complete for an implicitly fixed prime P, then there exists an extension of valuation rings of rank 1 such that the diagram commutes. Okay, so such a map is called a P-complete R cover. And so what we show with this P-complete arc descent is that if the rings R and R prime are perfectoid, then the cohomology of R with coefficients in G, or G of P power order, is just can just be computed on the check nerve of the cover. So if we take the iterated tensor products of over R, I mean derived and P completed, then we have this formula. So it I mean, okay. So the flat cohomology of a perfectoid R can be computed in terms of the flat cohomology of R prime, and it is like a Cartan type spectral sequence that results from this, and so then we can really, and the point is that this topology is really weak. Like every perfectoid can be covered by an R prime, which is just a product of valuation rings with algebraically closed fraction field in which a perfectoid rings each one of them. And so by using this, we can really make computations by hand in the end, in some sense.
You just erased what I think is the answer, but where is the LCI property required and not just depth?
So it is required in something that I didn't talk about, in this insymptotic Andres lemma. So I've mentioned that what we really reduce to is R infinity modulo a perfectoid modulo a regular sequence. And roughly speaking, what we want to do this Andres lemma is just a statement somehow that we can further reduce to the case where each of these FIs have compatible p power roots of in the ring. And we want to reduce from this further to the quotient where we extract those p power roots. And in this step, we use deformation theory, and it's in the properties of the cotangent complex and deformation theory that the LCI condition becomes like really, really important. And in fact, well, I didn't talk about, but deformation theory is another really major ingredient in improving these properties of FPPF cohomology, especially in the derived setting of simplicial rings. It's really, there are two inputs to these, which is the Dieudonné theory over perfect schemes, a special case of this prismatic thing, and deformation theory, which, well, of simplicial rings is as in Ulysses LNM volumes, and I mean slightly more generally perhaps. But okay, so yeah.
More questions?
Wait, microphone is on.
Everything is broadcasted.
Okay, so very naive question. You work with FPPF cohomology, FPPF topology, and would it make a big difference if we worked with symptomic?
No, in fact, if we have a finite flat group scheme, one can show that FPPF cohomology is the same as a symptomic cohomology. In fact, I mean, similar technique. Well, for instance, in degree 1, where it just torsos, it amounts to the statement that G is symptomic itself. So every torso is symptomic and is already captured in symptomic topology. In fact, in a proof, sometimes it's useful to pass to the symptomic cohomology instead of FPPF.
My question is that then it would be related to crystalline things.
Yes, I mean this relation. I mean this formula is very much in the symptomic spirit. It's yeah.
So in your theorem 4, if the classes, the torsion classes in H2 you have are given by PGLN torsors, can you say something about the class you get? Are there PGL torsors as well for some n that you have control on or something?
You mean somehow in this argument where I was doing tilting to positive characteristic?
Yes, if you consider PGLN torsors instead of torsion classes and try to say something. Yeah.
That is very difficult to control. I don't know is the answer. The proof is really cohomological somehow. If one starts with a PGLN torsor and follows through in the argument and obtains something in positive characteristic, then I mean I don't really know what is the There's no tilting for like vector bundles and stuff like that, so it's not.
Yeah. Thank you.
More questions?
Where? Yeah, that's here.
So I guess one thing I'm wondering is, are there any applications that you're hoping for, like in Brauer-Manet obstruction? Would this make certain computations easier?
I don't know. I mean, in some sense, it's a question for you, right?
Okay.
No, I mean, it's a general statement that could conceivably be useful in applications such as Brauer-Manet obstruction, but it's not such applications that really motivate us to pursue the statement.
Okay, and I was also just wondering, when you said over any ring R, is P related to R?
I mean, the answer is is no, really. I mean, one can omit this condition to begin with. It just, I ran out of time, but later I was going to state the p-adic continuity formula where the P would play a role, and roughly speaking, it says that if one has this R gamma, then it's computed in terms of the R lim of the reductions, derived reductions modulo powers of P, and it's an input to the proof, and okay.
Okay, thanks, that's fine.
More questions? There were a lot of. So I think that we can thank the speaker again.